think we're at the time. I don't think I'll be introduced. I think we're just good to go. I'm Ben. Hey guys. I really like reversing stuff with Radare2, and I'm really excited to be here and talk to you guys about some Radare. I hope it's going to be good. This talk was like originally delivered at DEF CON. Yeah. Hey.
Guys, it's starting.
Hey, we're starting the other talk, guys. Yeah. Merci beaucoup. Au revoir. Okay. So this one was originally like at DEF CON Car Hacking Village. It was like a 25-minute talk, but you're not all car hackers. I mean, actually, show of hands, are there car hackers in the audience? Oh no, so I can't bullshit everything. Oh no. Okay. Well, there's gonna be some bullshit. No. So I expanded this to an hour so that there could be some like introductory material into just how to get into vehicle hacking, relevant references, things like that. Okay, so it'll be like, first half is gonna be nice and gentle and here's all the good things you can do. And then the next half is just gonna be like, fly, bitch. Yeah, because Radare2 has this very steep learning curve. And if you wanna get into Radare2, highly recommend it, but there's a lot of material out there that's that initial look at Radare2. And what I really wanted to do was do a like, how do you take Radare2 and use it on an arbitrary binary firmware file? Which is something that like, you know, the author of Radare has done in a talk, which is great to watch. But there's not a whole lot that's like do the hard thing. And so this is really do the hard thing in the second half. So fair warning, the second half is not friendly, but I will try to be friendly in the first half. Okay. There you go. That's what I was supposed to say at this slide. We're good. So first up is just, you know, vehicle buses. Now, there's a lot of different buses going around in vehicles these days, but still one of the most common is the CAN bus. Okay, this is controller area network. It's a pair of wires. It uses differential signaling. Differential signaling lets the ECUs that are, you know, on this bus be resistant to common mode interference, right? So like if you receive radio signals, if you're doing differential signaling, both of the lines get the same EMI, the same electromagnetic influence, but because you're doing differential signaling, you just subtract it out. And you'll see differential signaling in a lot of protocols like HDMI, things like that. But this is, of course, you know, from the 80s, and it runs super slow. And the size of the frames is super small, but everything still kind of works. They pack it like this. They add another really interesting arbitration mechanism. So like if you think about Ethernet, it's kind of got that collision detection and backoff. What they do here is the arbitration IDs are prioritized. So like arbitration ID 0, if you're to send that out, that's the highest priority arbitration ID. These aren't like destination addresses, like MAC addresses you would find in Ethernet. These are more like functions. They're more like what the frame is supposed to represent, like a semantic marker, okay? And what happens when you do these transmissions is the person doing the transmitting, sorry, the node doing the transmitting, is responsible for actually reading whether the bit they asserted was the bit that was on the bus. And in this way, all of the transmitters can actually detect if two are talking at the same time. Because you can see 0 will always be like dominant, and you can detect if someone is asserting a 0 on the bus when you're trying to send a 1, and if so, you back off. And that way, that's how they manage, you know, multiple access onto the same medium. So that's important to remember. There's like a really dumb attack on CAN buses where you just send arbitration ID 0. And because that's the highest priority thing, you just DOS the bus. I mean, DOS is not very interesting, but this is kind of the way that, you know, CAN works, and it was designed to work. If you want some super cool details, it turns out that if you are going to like mess with these CAN frames, because 0 is a bit that can overwrite other bits on the bus, these guys here at Grim built a tool called the Cant, and it will actually GPIO toggle the bus fast enough so that it'll actually corrupt a frame in flight. So you can make these little pattern matchings and say, if I ever see this arbitration ID with like these particular bits, just as the last bit comes along, it just clobbers the frame and denies it. And they can do man-in-the-middle attacks on CAN by having a node on the side by corrupting the messages. So if you really want to get into the gory details, I highly recommend their talk from, I think it was Usenix last year. Super cool. So these CAN frames are flying around your vehicle. You have a whole bunch of ECUs all connected together. And it's important to remember, like, why did they even bother putting a CAN bus in a vehicle? So before CAN buses and ECUs, you would have, you know, multiple sets of analog signals going back and forth in the vehicle, okay? And these analog wires would carry individual signals, like whether your windows are up or whether your door is closed, or like where did you have your foot on the accelerator pedal? In some cases, otherwise it's vacuum pressure, but in some cases it's like measuring a particular signal, okay? By putting CAN bus in these vehicles, they took like the 32 or 64 wires that are necessary and just turned them into 2. It's like a weight saving thing, right? and then they time division multiplex all those signals into frames. Okay, so what I'm trying to show you this picture here is like, there's these time varying signals that people want to capture and do processing on in the ECUs, because that's kind of how cars work. And they want to be able to have multiple signals going down the same CAN bus. So these arbitration IDs can identify groups of signals, and then the actual signal is represented in the same bit fields in the same arbitration IDs over time. And that's how you like realize these CAN signals. This part is important because that's what we can try to extract from Openxc. And that's like the second half of the talk. You know, why would you bother? Because manufacturers don't tell you what these signal mappings are. There's a lot of different ways you can reverse engineer them. Some of them is like you get an instrument cluster and you just see what the dials do when you send it signals. Some of it is, you know, you take something you control and then look at the traffic and you can try to do correlations. And if you want to learn more about stuff, I'm going to give you a resource here, more ways to do that. But one of the ways we're going to talk about in the second half, reverse engineer some firmware and look at the mappings in the firmware to figure out where the signals are. All right, that's why it's relevant. Okay, so let's say you want to get started in some vehicle research. It's kind of fun. Where do you start? Honestly, you got a lot of reading to do. I'm sorry, but this one is free now, right? So Craig Smith made this seminal book. It's a free PDF. If you want to get into vehicle research and you haven't read it, you're doing it wrong. You should just be reading this book. It's totally free, okay? Also, there's a lot of really good references out there. Wikipedia is obviously a wicked reference for everything. Don't forget it. There's also an automotive wiki and has like some nice details. For example, I don't know if you're here in the morning, we were doing like this riskier challenge and part of it involved UDS. We got like all the references we needed for the UDS protocol just in the automotive wiki. So great resource with lots of details. I also recommend for learning stuff, like take some classes, CAN bus hacks classes. This is Robert Leali who teaches these for the most part at Black Hat. They're excellent classes, totally worth the time. He's a really good instructor. And of course, there's a lot of DEF CON videos out there. You should watch them. Shameless plug, I got one of those, you know, you can watch mine too. I would appreciate that. You're gonna want to tool up, okay? Especially you have a vehicle, you're gonna want to connect to it. Now, if you're the kind of person that really wants to live in Windows and like kind of likes to connect to Arduino consoles over serial and stuff like that, you could totally get Arduino shields that are CAN bus adapters, and you can like have a little Arduino serial connection and do your CAN busy things. You can also do like the Linux option where you actually have a CAN adapter in your Linux VM, and these are USB to CAN adapters. The two that I really like are USB to CAN and the Peak CAN. They're not cheap, they're not sub $100, but they are worth the money. And then you can use Python or Ruby or whatever you like to do your CAN traffic right there in your Linux host. That's kind of your two options. In Windows as well, if you want to have like the nice Wireshark kind of view of things, then you're going to want to like buy some software like Intrepid's Vehicle Spy and get some value CAN adapters, and that's like a path you could take as well if you like that Wireshark kind of view. Also, get yourself a logic analyzer, right? Like Celea logic analyzers are not really that expensive, and they will decode CAN. And sometimes you're going to plug your CAN bus adapter in, and all you're going to get is just error codes back, and you have no idea what's going on. And there just isn't enough debugging tools out there other than a logic analyzer to save you. So if you really want to like be able to figure out why you can't capture CAN traffic, you're going to need to go to a logic analyzer, so get yourself one of those. And of course a multimeter, just because, you know what, don't connect your CAN adapter straight up to 12 volts. It's just a bad idea. So, test the wires that you're going to connect up to first. Safety tip. Right, what else should you do if you want to get involved? If you're a student, there's a lot of really great things for you to do and learn. Okay, Car Hacking Village is at a whole bunch of different conferences, so I highly recommend go to cons, go to the village, just try to mess with stuff. There's also 2 challenges that go on annually that are specifically directed at teaching students that maybe aren't necessarily cybersecurity experts how to become vehicle cybersecurity participants, like people that can contribute, okay? The first one is the Cyber Auto Challenge, and the second one is the Cyber Truck. One of my personal interests is in heavy vehicle cybersecurity, so I have the pleasure of teaching at Cyber Truck every year. It's really fun. I love that event. And if you're a student and you want to just get involved in vehicle hacking, the technology between heavy vehicles and passenger cars is totally interchangeable, so I would just apply to both. Both of them have travel stipends. You just need to get like a letter of recommendation from one of your profs. You do have to give up like a week of your summer, which is maybe not so great if you're a student, but it is a really great learning opportunity. And really, it's the same thing for the pros. Even if you're not like a vehicle researcher, a lot of the people out here, I see some of them already that are, subject matter experts that could totally be contributing to vehicle security and teaching kids. Like for Cybertruck in particular, we have kids come in that aren't necessarily CS majors at all. Some of them are just mechanical engineering students, but they want to be at the intersection of both, vehicles and cybersecurity. So you can go there as someone that, is really good at doing network penetration testing. And I will assure you, I can't give you any details, but network penetration testing is 100% relevant to vehicle cybersecurity with trucks. And I can't give you a whole lot of details, but it is. So like, if you just want to get involved, teaching people is also a really great way to learn. So I'd highly encourage you to go and volunteer yourself as a mentor at one of these things too, because you'll be surprised what you learn just being involved in the exercise. And they need our help. They do. Right. So now you know everything, and you got all your tools, and you're ready to go. What's some things that you should try first? First up is head units. All right. So head units in vehicles are really, really soft targets. I'm showing you here an example architecture that we kind of put together that exemplifies a whole bunch of common things that you find in vehicle head units. They're often built on Linux. They often have a whole bunch of user space processes running under the same user, communicating over something like dbus or some other internal IPC. They have a whole bunch of peripherals, some of them at high privilege levels. Like maybe you can't resolve that, but sometimes you run into things like cellular modems that are connected to the SoC over PCIe, right? That's a bus master capable device. So the opportunities for exploitation and privilege escalation are right. And if you just want to be take your IoT hacking knowledge or your kind of just penetration testing skills, you could probably get a head unit and just start poking at these things and stuff will follow. So these are easy targets and you don't have to do a whole lot of CAN bus stuff to still get involved in vehicle hacking. So I recommend head units, something to try. Another great thing if you really want to understand vehicle networks, and this is right out of the Car Hacker's Handbook, is try to simulate or drive a gauge cluster. Write a piece of software that'll move the needles based on traffic that you see, or move the needles on a cluster that you get from a car wrecker by sending traffic to it. And this will just teach you about what are the relevant signals, how often you have to send them, what happens with error codes. You do learn a lot doing this. And it forces you to set up a CAN bus, okay? Or you could do the amazing thing and wreck a car or get a wrecked car and actually extract the whole vehicle. And this isn't the only instance of it, but this one's really cool. It's like putting a vehicle on a board. And they did another version of this recently, that's grim, where they got a car, and rather than having the wrecker extract the components, they went and took the wiring harness out themselves, because the pro tip is that if you have a wrecker give you modules out of cars, they just take a hacksaw to cut the wires and then give you the module, and then you have to figure out how the wires go back together. But if you get a car and actually take all the wires out yourself, you will save yourself time and you'll end up with literally an entire research station on a board that is a vehicle, which is kind of cool. So you could check that out as well. Finally is, messing with authentication. So these ECUs, there are some neat features. They allow reflash, you can dump memory on them, you can kind of look at key material, but they're not completely wide open. Well, we'll get to how wide open they are or not, but they have this mechanism for unlock. It's not a password. It's a challenge response mechanism called UDS. And if you're going to try to do something interesting with these ECUs, you're going to have to deal with unlocking UDS, which is Unified Diagnostic Service. And I'm going to talk to you more about strategies for how you might defeat UDS. So that was the easy introductory material, and now we're going to get a bit technical. The first thing I'm going to talk to you about is how you might deal with attacking UDS if you just have an ECU in your hands and you want to unlock it. And then remember, after that, I'm going to go into Openxc reversing with Radare2. So UDS is a diagnostics protocol. It also specifies a transport protocol. So if you think about how TCP is built up out of multiple fragments on whatever medium it's being sent over, part of UDS is something called ISOTP, and ISOTP knows how to reassemble the really small CAN messages into a stream of bytes. So remember that UDS is now a stream-oriented protocol and not those little frame-oriented protocols. It kind of makes things a little different. And pretty much all vehicle diagnostics in passenger cars actually rely on UDS. So if you have one of those little Bluetooth adapters and you have the Torque app for your Android or something like that, or maybe you have a scan tool, those things are all using UDS to scan the fault codes in your car. That's why UDS was created, is for those fault codes for emissions tests. But it's grown because once you put a feature in there that's kind of extensible and has that transport layer, the automotive engineers just start adding things on top of it, right? So now UDS has things like reflash and dumping memory locations. So all the fun stuff, right? You're going to want to unlock this thing. The authorization is done with something they call seed key exchange. I think if you know cryptography, you're going to recognize it as a challenge response mechanism. Okay, I have the hex values there if you're interested in those right now, and it will tell you if you got the answer wrong, which is kind of helpful, right? Makes things easier. Here's a nice diagram of how the seed key exchange works. You kind of tell the ECU that you're ready for a seed. That seed is supposed to be like a totally random number, and then you're supposed to do a calculation and send them the thing to prove that you know the secret. They do the same thing on the other side, and then they compare it, and if you knew the secret, then you're good, right? We're going to get into how that kind of goes wrong. So remember, why you care about UDS authentication is what you really want to do is unlock one of these ECUs. These unlock mechanisms are buried usually inside diagnostic software, like running on a Windows PC connected to some scan tool in a service shop, right? So you're really trying to pirate the ability to unlock these ECUs. So I like attack trees, and I kind of make an attack tree here just to break down all the different ways that you might go about pirating the UDS session. I don't have to bore you with the notation, but the red stuff is easy for attackers, and the blue stuff is kind of hard for attackers. I'm going to go all the way down to the weird things like glitching past the checks when we're talking about how you might kind of bypass or unlock UDS. So first up is UDS is a 16-bit challenge response, which means that you can actually extract the lookup table for this thing, right? I mean, you can, if you have a diagnostic software, you can fake being an ECU and just keep sending different seeds and actually just extract the entire lookup table and then take that, and anytime you want, you get a UDS session. But of course, you need that software and the time. This is a great example of a student who just set up a 4-way extraction of all the challenge responses to get it done in a week, which is pretty cool. You can also reverse engineer that algorithm, right? So diagnostic software, in your garage knows how to take a seed, a challenge, and turn that into a key, a response. So you can just open that thing up in dnspy, because it's probably written in C# or something, and get that algorithm. There you go. Now you can unlock it yourself. Or you can kind of do the dumb thing and brute force it. So brute forcing sounds like it might be kind of hard, but remember this is just a 16-bit challenge response, and maybe you can control the seed. Or maybe the seed isn't really random. So this is actually a picture of the x to x plus 1 relationship of seeds. Okay, so what you should see for that is a block of blue. If anyone's ever seen random number generator tests, when you look at the random number generator that's good, it just covers the entire square, right? What you see here are these extremely strong linear relationships. So if you saw a relationship like this coming out of the seeds on an ECU, you might even be able to, do a linear regression modulo a certain number and just get the answer back out. So brute force sounds like it's not a great idea. The truth is that, the actual crypto that they put in these ECUs is not really cryptography. So you're not in a really bad place to try that approach, okay? Another thing that happens is people who make these ECUs will have the same algorithm, but then when they do different models, they'll change the parameters in the algorithm. So if you've run into the algorithm before, you can just go and kind of solve for unknown parameters. There's a great blog post from Enigmatos where they did exactly this, and they found they could just take 10 seed key exchanges. So that meant that they only had to take their car to the garage 10 times, capture 10 exchanges from the garage tool, and then all of a sudden they know all the parameters. Right, remember that's the thing is you can install your CAN bus sniffer and then bring your car to the garage and you will see the seed key exchanges from the tool, right? So 10 is a totally reasonable number for this. And then of course you can glitch past. And if you saw my talk this morning, I love to do glitching and hardware modifications and stuff. So this is my favorite thing to drool over, but it's kind of weird, right? Because remember it's a seed key exchange, you have to send the response, but then there's all this processing that happens before you really would know where you could apply that right glitch. And when you're trying to do glitching, you really want to have determinism of where you can put it. So trying to glitch from the context of I sent the response and now I have to wait this amount of time will never work because the jitter adds up too quickly. The smart thing that Riskier did, and they talked about this year, instead of trying to glitch past the authorization step in seed key exchange, go to one of the really important functions you want, like read memory, for instance, and just glitch at the read memory operation. Because somewhere in that code, the read memory operation is going to go and check a bit that says, am I authorized? Just glitch the am I authorized check in the function you're interested in. Don't glitch UDS itself, right? So in summary, UDS is not really locking down ECUs as securely as maybe they should be. Your mileage will vary. There are OEMs out there that have much more sophisticated protections on their ECUs than just UDS. So be careful, pay attention to what you're looking at, and don't waste your time when you run into something that's weird. And try some of the cool stuff. Okay. So we're into the second half, and it's not going to be as friendly. I'm going to just dive right into Radare, and we're going to look at a lot of disassembly and stuff. So this was at DEF CON before. I made just a tiny couple changes, but it's pretty much the same thing. First up is Openxc, right? So I said I'm going to reverse engineer some Openxc binaries. What is Openxc? Ford makes these dongles. They're kind of like we talked about socket can adapters, except that showing up in Linux as a USB device, these things show up as a Bluetooth device. And then they defined a protocol over Bluetooth using JSON so that you could develop an app, say for your phone, that knows very generic names for certain signals like tire pressure or velocity or something like that. And then the app could be the same, but you could have different cars, right? So I got the same app, but totally different models of Ford, and the app would still work with all the Fords. So it means that these dongles actually know how to decode a whole group of messages, and they know a mapping from like a very specific car model's thing to a really generic name like tire pressure, which really, if you're trying to figure out what a CAN signal is, that's the info you want. So it's a hardware platform and a software SDK. It's actively developed. They're kind of cool. I encourage you to check them out. They're a neat little device. Right. There's a different firmware for every car, right? So that's another flag to us. That means that they are actually encoding in these firmware loads very specific details about, the vehicles that they support. And finally, yeah, they're communicating this stuff over JSON. So that also means that in that firmware is a mapping that's like this particular bit field has this really descriptive name. So all the things we kind of want for a signal are there in the binary. Right. What is Radare2? So show of hands, has anyone heard of Radare2 here? Excellent. Has anyone used Radare2? Great. Okay, good. Awesome. So if you use Radare2, you know that, if you open a normal ELF file, so here's like, I'm showing a session of me debugging Radare2. I kind of wanted to do like the live console thing, but the more people that watch me type, the slower I type. So I think the presentation would probably take like 2 days with all these people watching me type. So I have like this fake PowerPoint me typing thing. So I opened up this binary. It turns out to just be one of the ones from the binary samples repo in GitHub. It's, just ls. And I do AA, and AA is the Radare command for analyze mostly everything, just the basic stuff. And then all of a sudden it says it made these flags, okay? Remember that. So I did an analysis, and all of a sudden it created flags. Not the flags that we love, CTF players, Radare flags, okay? And then I'm S main, so that's me seeking to a function called main. And now, after I do that, you can see that my address changed. See the red thing there, the red prompt? It's kind of like, your PS1 output at the console. It tells you what address you're at in the binary, because everything you do is contextual. You have a cursor, and the red thing is telling you where your cursor is. And then I asked Radare, okay, AX, so show me cross references, tilde main, but grep the output of AX for main. So the tilde, that's the grep operator, right? So I'm grepping the output of a command AX for the string main. And then I really just want to look at the top, and Radare does have a way to just do head, but I'm showing you also that you can just use pipes. If I put a pipe into a Radare command, it will do like the shell thing and spawn out to an executable and pipe it through a pipe. So it did the normal thing, right? And what I'm looking at here are the first 4 cross references from the binary to the function main, any code in the function main. So this is like the bread and butter of IDA. It's hitting the X button. Like, show me those X refs. That's all I really care about. I just did that here. Okay? And then Q, I'm out. So really the point of this talk is that when you open up a flat binary file, and what I'm looking at here now is Ford's open source firmware for the Openxc. It's an ARM binary file. We're going to talk about this at length. But I'm going to try to analyze it, right? And it says it made some flags, but it really didn't. I can't seek to main. This is a flat binary file. It doesn't know main. There's no symbol information here. So really, when you're using Radare to reverse engineer like a flat binary file, the best you can get is Clippy's help. And this is a fun Easter egg. You can do $! E and it'll show you Clippy in case you feel lonely while you're reversing. Yeah, might come in handy someday. Radare also does some really gorgeous stuff, like when it's doing disassembly of stuff it knows about, it can show you the control flow graphs in your terminal, which I love because it's copy and pasteable, and you can actually change the sizes, and it's using end curses, so when you change the size, it changes how big the things are, and you can zoom out. So, the control flow graph view in Radare is really great to use. Unfortunately, I'm not going to talk about the control flow graph view, but if you want to use Radare, this is a good reason to do it. What I am going to talk about are all these commands. So I've gone through the presentation, I kind of extracted all the commands I use, and I'm just going to go over briefly because really these slides are available later, and so is the recording, and you can totally go and check this in detail. But some of the important things to take away from this slide is that all these commands are grouped hierarchically, right? Like the first letter in the command is a category, and then the second letter is usually like a specific invocation of that category. Sometimes it gets deeper than that, and the actual command is 4 down, and it varies because Radare is complicated, but there is categories. So A is obviously like analysis, right? The P's are for printing things. The T's are for your type information. The question mark is inspection, like give me information back. We have I for information about binaries. C are comments. There's the tilde thing for grepping. And I'm going to show this slide again right at the end so that maybe the one that you saw that you want to know about, it's going to be right at the end of the talk as well, okay? So, funny picture break. You guys have been a great audience. This is going slow, I know that, and it's not going to stop getting technical. So what I'm going to do for you is I'm going to give you 3 funny picture breaks in the middle of all this disassembly, okay? All right. So remember, Openxc is taking JSON definitions of what a signal is, like tire pressure, and encoding that into some kind of a binary structure that's in those flat binary files. And what we want to do is reverse this arrow, because if we can reverse that arrow, then we can drive our own custom cluster, or maybe you could make one of those cool oil temperature gauges or turbo gauges that you pay an extra 20 grand for an ST or something like that. Just make your own, right? Okay. I didn't do this by myself. There's a whole bunch of prior art that went into this kind of work, standing on the shoulders of giants and all that, so I want to mention some people. This guy, BSMT, he did some reversing of Openxc that's totally relevant. If you're talking about just doing firmware reversing, Craig Hefner has taught me a lot of stuff, and his blog is amazing if you want to learn about reversing firmware. And of course, Radare, I didn't write Radare. I can't take any real credit for that. The guy who did has given a talk on reversing binary firmwares that I recommend you watch because he's brilliant. Okay. So our plan, again, if you're going to reverse an arbitrary firmware someone gave you to get some information out of it, you're going to have to sort of go through these steps. And I'm marking in blue the stuff that we're not going to do in this talk because then the talk would be too long. And also the stuff that's in blue is from a different talk, so you can go back to that prior art in BSMT's blog. But I am going to talk about the stuff in yellow. So you're going to get that firmware. You're going to figure out what architecture it is. You want to figure out where it's loaded, what's that offset. And then actually get that in the right offset. You want to go and find loader loops. If you've done any C programming, the CRT, the C runtime, it goes and finds that data segment, it copies it in a RAM for you, and you want to actually emulate that, because if you don't put your data stuff in the right location, you don't get XREFs. If you don't get XREFs, you will not be happy. And then finally, because we're trying to figure out what these CAN signal definitions are from the JSON, we want to pretty print these structures, because we're humans and we want to look at human readable things. Stands to reason. Okay, first up, how do you just take a binary file and just load it in an address? So that's actually pretty straightforward with a Radare command. There's a -m that'll change the load address. So here's an invocation. I know it's ARM because we already figured that out. I know that it's thumb mode, that's what B16 means. And I know where the offset is because we read the data sheet, we did the right homework, and now we figured that out. So you can totally just load your binary in like that, and you're done. You don't necessarily want to do this iteratively. The reason being that as you're trying to explore this binary, you're going to find that you need to make little tweaks. I knew all this invocation from hard work where I kind of learned the mistakes. But when you do this with a brand new binary, you're not going to know right away. So what I recommend you do is make a .r2 file. Make a file that's saving the session setup for how you're going to do reverse engineering. So what I did is I translated that command line invocation into some E commands, all right? The E command in Radare is all about setting configuration values. So I'm setting up Radare with all the right config values. It's ARM, the processor type is Cortex, 16-bit in Radare's context means thumb. even though, we all know thumb and 16-bit aren't exactly the same thing. We're setting up the binary address and the flash address, giving it the file. At the bottom, I have like ON, and this is where I'm actually opening a specific file. And with Radare, you can open multiple files. So like if you had this weird firmware that came in like multiple segments, you could have one of these config files and save the multiple segment files as individual files. You wouldn't have to use DD to put them together a weird way. You could just put them into the virtual address space using this config file, right? You set up VA. IOVA is all about virtual addressing. You're going to want that because remember, we're doing weird segmentation with the files. And then S is for a section. So finally, we're just telling Radare that, this part of memory has executable bits and it's this big. And let's go, okay? So you can see that now we're going to like evolve this .r2. I went from stage 1 R2, now I'm going to do a stage 2, and I'm going to use stage 3 as we go on. You'll see it evolve. Also from previous work, we know like the loader loops. This is kind of like the C runtime stuff. I know that it goes into that flat file in Flash and copies it from this yellow address to this blue address, and I also know the length of it is orange. So I'm going to put more stuff into our config file. Oh, of course. Can you see that? Yeah. Bummer. It's okay. It's in my recents. I'm sure it'll be fine. Okay. 1 second, please. I think this happened before, and I had to actually skip the slide because it kept crashing again on the same slide. So this time I'm going to be smart. I'm not going to make that mistake. Maybe. Well, we'll find out. Right. So I'm looking at a little icon. You can't see the icon, but I just want to say what we did was augment stage 2 R2, our little R2 session file, with the information that's copying that file. We're remapping the same file into a new location. So you're like emulating the loader loop, right? The loader loop copies the data to a new location. You just turn that into a Radare command that's like, open the file and put it at this address from a certain segment. That way now, when you're done, it's almost like you're analyzing the state of memory after the loader loop had executed. And that way you get your cross references. Okay, so I'm gonna skip that slide. We're gonna go to one that won't crash, hopefully. Okay. So now what we have is the binary is loaded into the right base offset. We have our little piece of the data segment now up in RAM. And so ideally, because this is what we love in reverse engineering, we want our cross refs, right? I want to be able to look at a value somewhere in RAM and see who's referencing it, because otherwise, how am I going to figure out where the relationships are? So let's like kind of inspect what's going on in this current state. So I've invoked Radare with -I, and that like runs that session file. That's it. Everything I did there is now saved. So you can imagine, as you're exploring this binary file, you could just iteratively be running Radare with -I, tweak the file, rerun it, and that way, you're not going to lose your work. We know where the signals start from previous research, so let's just put that in. I'm using the F command. This is flags. So remember, these aren't CTF flags. Radare thinks that flags are the namespace. That's just what it calls them. And it does this interesting thing where it puts like hierarchical names. So strings are like str dot something, and symbols are sym dot something.